design quantum circuit for a Hamiltonian. If we are given a Hamiltonian, how we can prepare a quantum circuit corresponding to that Hamiltonian. Okay. So this is a Hamiltonian of a quantum router. Just let me write down. In our previous lecture, you could find a lecture on quantum router where we have discussed about the Hamiltonian and how does it work and how the circuit works, and then what are the lectures. We have already discussed about those things. So here in that lecture we did not show how we design the circuit explicitly. So in this video we are going to explicitly design the quantum circuit. Okay. So let's go term by term and prepare unitary operator for the corresponding Hamiltonian. Okay. Suppose we are given in Hamiltonian, in Hamiltonian which governs a particular system, then we need to find the unitary operator corresponding to that Hamiltonian. So the unitary operator will be So it is exponential minus ist, and t is our time. I mean, for the time interval, we want to see the we want to see the evolution of the state and evolution of the system. So we can find the state of the system at a particular time, psi t equal to u of t psi 0. So psi t is the state of a quantum system or a system at a particular time t, and we'll get that state by applying the unitary operator on the initial state of the system. Okay. So here you can see in the Hamiltonian there are so many terms. There are several terms, like here we can see 1, 2, then 3, 4, 5, 6, 7, 8 terms. Okay. So when given in Hamiltonian there are several terms, we need to decompose the Hamiltonian into so many terms. So, for example, in this case, suppose our Hamiltonian is like h1 is plus h2. Suppose hn terms. If in Hamiltonian we have n terms, then the unitary operator will be we can write this term when so this expansion is not true always. I mean, when h1, h2 and all the terms commute each other, then we can write the expansion as follows. But when the terms do not commute, when h1, h2, h3 they don't commute, we can't write it like this one. So for that we use Trotter decomposition. So what is that? If they are not true, I mean h1, h2 combination not equal to 0, h1 h2 combination not equal to 0, h1 up to hn combination not equal to 0, then we can write this term as now you can see we have only see we have taken small time interval t by n, t by n, so we can write it t by n as delta t. So this is actually the minus side. H1 delta t. And we need to repeat the whole thing n times. And when n tends to infinity, I mean we need to take n to be a large number, and as much as we take the n value as large, we have that much of accuracy in the results.
This n is same as the number of Hamiltonians, h1, h2, hn.
No. I mean is here, yeah. So I may write down something like n. But here also n. So n might be, do we take n as a large number? Okay. So this is the Trotter decomposition. When? So we need to write the Hamiltonian, the interoperator, the whole interoperator like this one. When the terms, I mean h1, h2, hc up to hn, they don't compute each other. Okay. So now let's design the quantum circuit for this Hamiltonian, and we need to, and here we can see that, I mean we can check that sigma 1z, sigma 2z, and all the terms commute. But after that they do commute. If they do not commute, then we need to use Trotter decomposition. Then I can write it here. Okay. So now let's proceed. Here we can, one thing we can see that, I mean here you can see when the terms commute, then also we are going to prepare the same kind of terms like e to the minus I h1t, h2t, h1 hnt up to hnt. And when they do not commute, then also we need to write the terms are like that, h1 delta t. Only the parameter changes. You can see the parameter only changes. Otherwise everything remains same. That whole integral operator need to be repeated m times, and m is a large number. So for large number of times we need to repeat the same thing. Maybe I can show. I can show like this one. Suppose an integral operator is like a box. Suppose this is a box, and there are two boxes. I imagine that there are two terms in Hamiltonian. So there will be two integral operators, u1, u2. So if the terms commute, then we need to only put those only, two integral operators correspond to that two terms. But if they do not commute, then we need to put the same operators. The operators are exactly same, but the parameter changes only. Only there will difference in the parameters. So the parameters will changes, and it has to be repeated m times. Okay. Now let's assume that in this term all the terms commute. So you can check that whether they commute or not. But now let's assume that they commute, and let's prepare the inter operators correspond to that Hamiltonian.
How do you decide what would be your m?
M we can take. Actually, there is no decision. You can choose m at any value. You can take 10 times, 100 times. You can choose m at any times, but according to your architecture. Suppose in architecture there is a space problem. There is a space limitation. You can't take up to 100, or you can take up to 1000. So as much as m you can take, you will get that much of larger accuracy. But you can choose accordingly for your perform the experiment. In which architecture perform the experiment. And also in the real chip, if you see the real chip, as much as your m will increase, you have that much of errors. So in general, in the experiment that we have already done, in some cases we have taken at m to 2 times, 3 times, 4 times. Also we have taken like 100 times in some of the cases. So according to our choice, we can take it. Like when we are simulating on a simulator, we can choose M as 100,000, we can take it. But when we are running on a chip, we'll take at least about 2, 3, 4 up to that. And also another thing is that in the simulator, in the simulator also in the real chip, when our circuit space is larger, then we are going to get results. I mean the time is delayed. I mean we get result after a long time. So it's better to take M to be a smaller value, and we can do up to value. I mean that suits our results. Like on that time, until that time we can wait and we can update the result.